I can get a simulation in a minute, literally on the phone going, that's how fast it is. But if we take the fluids, now if I calculate the heat transfer, then I can take the heat transfer and calculate the thermal stress. So from the thermal stress, I can calculate where the problem spots might be. We'll be able to take all this data and leverage that for making predictions, even without running CFD. So we can, since LBM is mesoscopic, you're kind of closer to the molecules. And if you think of machine learning as some way of predicting the future, well, M-Star is already kind of really good at predicting the future. And then you have all of this massive data sets that you can then leverage to predict even more stuff. Who knows what we'll find.
All right, Ben, welcome to the show.
Hey, thank you for having me.
Can you give the audience a little bit of an introduction? Like, who are you and what are you working on at the moment?
Yes, my name is Benjamin Turner. I'm the North American reseller of M-Star CFD. I work on a lot of different things. Right now I'm working on a replacement for a half-pipe jacketed reactor, but I also do a lot of different consulting work as well, everything from nuclear reactors to stem cell bioreactors. So my company LATTICEPT does regular consulting and engineering, and we basically take any engineering problem that's hard enough for us to be interested in, honestly.
That's a good summary. How did you first get in touch with M-Star? Because I've known the guys for a couple of years now. So what was the first interaction with the M-Star guys?
I don't actually know how I found M-Star, but I remember seeing a video, probably on LinkedIn, and thinking like, is this Blender or some type of rendering or something like that? But when I dug into it, I was like, oh no, this is like a fully functional CFD program. Then I reached out to John Thomas and he gave me a trial. That was basically my first interaction with M-Star. But I thought it wasn't real, honestly. I thought it was a rendering from Blender.
Going back to your education, how did you get first in touch with simulation in the first place? Did you start off with FEA or was it CFD first, or how did that happen?
Yeah, that's a good question. So in college, we dealt with FEA, but we didn't really, compared to what industry does, it was relatively minor. I originally started with a pipe stress analysis, which is basically one-dimensional FEA. You have beam elements. Honestly, I thought that was kind of boring. I was designing pressure vessels. I wanted to do something more advanced. I started teaching myself FEA, the Section 8 Division 2 code. So my first interaction was with FEA, but I was always interested in CFD because those were the hardest problems, which always interested me.
All right. I'll let you first take a sip of coffee because it's quite early for you.
Yeah.
Pipe stress analysis. Walk me through, like, what is actually, you said 1D analysis. What's actually the hardest part of doing? You mentioned also pressure vessel design, I think. Was that the next step then for you? So 1D analysis and then pressure vessel design was the next step for you?
Yeah. So I actually start off with pressure vessel design. So Division 1 is really just algebra. And I remember my first experience out of college was, this is it. Like, this isn't really hard. It was just a bunch of algebra. So I was really interested in pipe stress analysis because there's some engineering to it. You're routing pipes all over a chemical plant. You can't just go from A to B because the thermal expansion will cause them to fail. So you have to add some thermal expansion loops. So there's some creativity to how you do that. But yeah, they're one-dimensional in the fact that you treat every pipe basically as a beam, point to point, and you give it some, cross-sectional area, and that's how you calculate the stiffness, and there's rules to calculate the stress. But it's essentially beam-type analysis. There's no shells, there's no solids, nothing like that.
Got it. What was actually the hardest part in terms of FEA in simulation when it comes to pressure vessel design?
Yeah, we could talk about this a lot. So one of the harder parts of FEA is actually trying to interpret what the code says. So a lot of people, me included, will sit down and put something into FEA and think, okay, that's an FEA analysis. But the code has very specific ways of how it wants you to develop, through wall meshes, how you draw your stress classification lines. There's so many procedures. Really, the hardest part is knowing what the code wants you to do so you don't hurt anyone, basically.
I see. Okay. And then after, anything else you want to talk about in terms of pressure vessel analysis? Like what was actually the learning experience from that? Because I could imagine it was quite hard for you as a young engineer, but what did you actually learn from it?
Oh man, so much. I mean, the wealth really, I almost, if I could tell, the college industry something, it was to be more focused on actual industry standards, because the ASME code is thousands of pages of theory. PhDs have developed all this stuff. You have all the standard materials in there. Like basically, it's a huge data book of everything. And it's kind of sad that I didn't see this until I was in industry. Like this is how industry does all this different design. So you really learn one from pressure vessels how careful you have to be. Again, because we're building chemical plants, we don't want to hurt anyone. Two, you will learn quickly that you don't know as much as you think you do, because someone has already done this 100 times and has come up with the way of how you should do it.
I see. Did you have a mentor back then who was assisting you on your learning journey?
So I worked with a really good guy named John Thomas, which is interesting because there's now another John Thomas at M-Star, but the first John Thomas was his background was Westinghouse, so he originally came from a nuclear background where a lot of these rules were originally developed. But his background, he was a senior guy. Most of his background involved literally punching cards. So, his background is very archaic compared to a modern FEA software. So he knew the theory to some degree, but using the actual computer software was just kind of something I just had to figure out. There wasn't really a mentor to really help me. Yeah.
So you were your own mentor to some extent.
Yeah, and I think that's the most important thing in engineering. You have to just figure it out. If you're waiting on someone to teach you, you might get really lucky and have a mentor, but most of the time you just have to figure it out. Yeah, that's what I did with M-Star too. Yeah.
Yeah, that's true. I'm quite interested in how did you come up with the idea of founding LATTICEPT in the first place? What was the entrepreneurial spark inside of you that made you decide I'm going to start a company now?
Yeah, so it's a good question. Many people have asked. So I switched. So I originally started pressure vessel design, building hydrogen plants. Mm-hmm. When the oil market tanked, I left. We went from getting huge bonuses to oh yeah, we might not have any work. So I left and went into Hargrove, which is a consulting firm. And when I was at Hargrove, I was hired for a really large project for Eastman Chemical. And then when that project went away, the work wasn't again so. It didn't look good. So inside of Hargrove, I kind of developed what became what's now called the Advanced Solutions Group. And they focus on FEA and CFD. And I basically turned that into a business internally, selling to clients, FEA, fitness for service for chemical plants, stuff like that. So at some point, really, it was just kind of why am I doing this for someone else? I could do this for myself and make all the rewards and, without someone taking, most of the money. So that's basically really, there's not much to it. I'm doing this already. I'm writing the proposals. This is basically a business. I don't need to do this for someone else.
Yeah, that's true. How big is LATTICEPT now today? Is it 2-3 people or is it even bigger?
So we have 3 full-time employees other than me, and I have several contractors that I've hired all over the world doing different stuff. Yeah.
What would you say is the hardest part and the easiest part running a company?
The hardest part of running a company is that you don't actually get to do much engineering. It's a lot of accounting. It's a lot of budgeting and planning. That really is the hardest part of doing engineering. So then you spend 40 hours a week running the company, and then you have to work overtime to do the fun stuff that you started the company to do. So the hardest part of running your company is that you work basically all the time. In the beginning, at least, you're just working all the time trying to get the company going, get cash flow. I don't know if there is an easy part. I guess the easy part is that you don't have to listen to anyone. You are your own boss. You don't have to tell me when you're going on PTO. You just leave. No one to report to. Yeah. It's not for everyone, but once you do it, I don't think I can go back.
Yeah, it's the most enjoyable part of running LATTICEPT because actually I first saw you posting something from M-Star And I thought you were actually a CFD consultant, but you do actually way more than that, as you just mentioned, right? So it's not only CFD, you also do other stuff on the side.
That's right. Yeah. So I post mostly stuff about M-Star because it's so visual. M-Star makes videos. No one really wants to stare at an FEA analysis. It's not really as interesting as this process mixing or something like that. Yeah. So I focus mostly on CFD now because I sell the software. So it's a business move. Plus, I think it's fun to play with. I joke that M-Star is like playing with Minecraft, but it really is kind of like a video game. You can set up neat little models and watch how it works. It's pretty cool.
I'm not sure if it's Johannes, who is the kind of the post-processing guru at M-Star. Like he's the genius behind all of that post-processing magic, basically. But there's more to it, right? So it's also the speed of M-Star, which I think is very fascinating. So talk about that a little bit in comparison to the classical finite volume solvers like Fluent.
Yeah, okay, that's basically how I found M-Star. At some point in Hargrove, I was selling these projects to clients. They want them done in weeks, not years, literally. So I was selling stuff, maybe some stuff that I shouldn't have sold. That was just so slow. Even with hundreds of cores, cloud resources at my disposal, I was always looking for something else. I actually stumbled. So I have a patent for a chemical reactor. So you've got heat transfer on the inside, you've got agitation, and then there's fluid on the outside wrapping around the vessel. I tried to do this in Fluid, and I would have needed a supercomputer. I originally looked at Flow 3D, which was a really excellent software. I think they specialize in volume of fluid. Mm-hmm. And then I saw M-Star, and that's when I was like, this can't be real. So really what put me onto M-Star was how fast it was. Yeah, so that's basically what attracted me to M-Star. Once I got a hold of it, it's the real deal. It's that fast.
Yeah. I want to delve a little bit deeper into the LBM technology. So can you talk a little bit about the basics or what happens in the back end of M-Star?
Yeah, this is so Lattice Boltzmann is kind of it's completely different, and it takes a while to get used to. So if you think of finite volume is essentially trying to solve really stiff differential equations down to some convergence tolerance, right? You're trying to get the fluid pressure and the velocity and all that to basically converge, like a calculus problem. When your series get below a certain convergence level, you can say the differential equation is solved. It's universal, but it's also extraordinarily slow. So because you have all these stiff differential equations, well, Lattice Boltzmann kind of takes a mesoscopic approach. So if you think of Navier-Stokes being the macroscopic equations, it kind of takes a step back and mesoscopic. So now we're looking at basically we break up the whole fluid volume into individual particle parcels. And then we're looking at lattice speeds bouncing into each other. And so every simulation is transient and basically starts off at zero. And you can literally watch, the velocity basically, emerge from this simple Lattice Boltzmann solution. And so LBM is so fast and it's perfect for GPUs because we can just send each voxel to its own core, and then you can basically solve the fluid problem very quickly.
Yeah. One of the things that interests me is kind of the use case of the reactor design that you just mentioned, that you also have a patent on. Walk me through how easy it is to generate a digital twin using M-Star for that reactor.
Oh, it's really easy. So M-Star has all these built-in primitives. You just bring in a tank. You can apply a surface coefficient for the outside for the jacket, and you literally just press go. I can get a simulation in a minute, literally on the phone going, and I'm talking about set up. I'm talking that I can get results within a minute on the phone. That's how fast it is. And M-Star can import CAD. So I have an entire script written basically that develops so when a customer brings me the specs, I can type it into a Python code. The Python code generates the CAD. I bring the CAD into M-Star. All this is done with Python. M-Star has a Python interface as well. Yeah, and then I'm basically just generating fluid results very, very quickly. And we can do minutes of simulation, hours even of actual fluid simulation, which is crazy.
Yeah, it's really crazy. Sounds too good to be true. I think what we should do probably, Ben, is kind of a deep dive session, like a live demonstration, maybe streamed on LinkedIn and YouTube where people can just see how fast the solver actually is.
Oh, that would be crazy. Yeah, I think we should do that for sure.
Yeah, it would
Yeah.
be really, really cool. I think maybe let's talk about the put some emphasis on the benefits of building a digital twin instead of M-Star. Like, what are the actual benefits and the advantages of having a digital twin at your fingertips? Like, how can engineers benefit from that?
Yeah. So M-Star really took over kind of the pharmaceutical industry. That was like the first killer, industry because experimentation is extremely expensive. I work with some stem cell clients, and even if they have a very small reactor, the media just required to grow these stem cells to tens of thousands of dollars to just the fluid that the stem cells grow in. So being able to do all your simulation in a computer, when engineers drinking coffee at a computer compared to sitting in a lab, spending money, burning up materials, you can make sure that your problem is really well defined and you've got a decent solution before you ever cut a piece of metal or spend any money in the lab. That's the biggest benefit of digital twins.
So you're also able to do kind of predictive maintenance stuff and do some future predictions based on the digital twin before even building that thing.
That's right. Yeah, it's exactly right. Yeah. So if you couple, so let's start with the fluid. If we take the fluids, now if I calculate the heat transfer, then I can take the heat transfer and calculate the thermal stress. So from the thermal stress, I can calculate where the problem spots might be.
Mm-hmm.
So we can run all sorts of scenarios in a computer that you're just not going to do in real life. If you went to a Eastman Chemical or Dow and was like, all right, well, let's see what happens when we just start this up and shut it down real quick. No one's gonna do that in their actual chemical plant, right? That would be too dangerous. But you can do all that stuff in a computer and really start to answer those scenarios, those process upsets, and all that stuff. That's gonna happen. You just need to know what's gonna happen before it actually does. Yeah.
That is pretty crazy. Yeah, I really have to see that. Like, Johannes gave me one demo, I think, a couple of years ago. When I first saw it, it was like mind blowing. But technically, what that means is you could leverage the digital twin to also to fatigue analysis and even, I don't know, analyze weldings, for example.
That's right. Yeah. So when I first talked to John, M-Star had some heat transfer capabilities, but I really pressed John. I was like, John, this is incredible. He already knows it's incredible, but if we could really just nail thermal and heat transfer, that basically opens up oil and gas, all these other chemical industries where mixing is important. And the Lattice Boltzmann method is not just for mixing. People think a lot of the time like, oh, it's just no. It's a general fluid problem. So anyway, I convinced John that we could really focus on heat transfer, and he did. And now, we can take the temperatures of the static bodies, bring them into FEA, and do all sorts of thermal stress analysis. That is a huge problem because if anything fails in the chemical nuclear world, it's almost always thermal fatigue. It's either corrosion or thermal fatigue. That's like the 99% of failures. Yeah.
I see. Where does ML or AI come into play here to actually do some predictions?
Yeah. Some of this is secret, but yeah. So eventually we'll be able to use all those scenarios that we've run, leverage all this data. So M-Star produces so much data. It's almost, my new computers have 400 terabytes and that's just to save the data that I want to keep. We'll be able to take all this data and leverage that for making predictions, even without running CFD, so we can, who knows what we'll find, but basically since LBM is mesoscopic, you're kind of closer to the molecules. And if you think of machine learning as, some way of predicting the future, well, M-Star is already kind of really good at predicting the future. And then you have all this massive data sets that you can then leverage to predict even more stuff. I think that's the future, is going to be able to take Lattice Boltzmann simulations and then use that to predict even more. Another thing about how ML will probably play into Lattice Boltzmann specifically is these super scalars. I don't know if you've seen these super resolution things. Mm-hmm. So Lattice Boltzmann, at least M-Star specifically, uses all LES simulation. So it's a spatial filter. But what if you have one area that's not really refined? It's kind of one downfall of LBM. If you want to refine this area, you can do that. There's refinement, but you're also reducing the time step by a factor of 2. because you have a local time step reduction that slows down the program, right? Because you're waiting for the coarser LBM to catch up to the finer one. But in theory, we should be able to use machine learning superscalars to refine that little area after the simulation is ran. So you can take an LBM simulation, and then if you're focused on this specific area over here, you can use a machine learning algorithm trained on actual turbulence data to super resolve one area after the fact. So I think that's going to be a huge thing coming up.
Yeah, this sounds really, really cool. I think what we also have to put emphasis on is kind of the economic importance, right? Being able to predict the future would actually save people who run these plants an enormous amount of cost.
Oh, yeah, absolutely. Yeah. There's so many problems in industry. I mean, that's like, if you're a problem solver, people say, oh, well, if you want to, what industry really wants is problem solver. And that's true because there are so many problems. But what you also need to be able to do is communicate how to solve the problem. And that's where engineers usually aren't the best at. One of the hardest parts of running a company is self-promotion. Now, you're a marketing guy. You're good at promotion, but most guys aren't. You have to stand up in front of everyone and say, hey, I'm the best. And it doesn't come natural to most engineers, right? So, lost my train of thought. What were we talking about? I'm sorry. What was your original question? I'm sorry. I started talking about
the economic importance and financial losses.
Yeah. So having these tools also communicates to your managers. You can point to a layman. This is the problem. Not some complicated analysis that they're not going to understand, some 30 pages of calculations. You can literally say, well, here you can see that the flow is recirculating, or, here you can see the hot spot. So these visualization tools, we joke that it's colors for directors, but there's a lot of truth to that, because you can communicate to important people that don't know all the theory of what's going on. Yeah.
Mm-hmm. I'm wondering what is the future for M-Star or maybe LATTICEPT in this regard, especially when it comes to CFD? Because maybe the question should be, how is it being done today? Like, what is the status quo looking like in the industry? You mentioned corrosion and thermal being a huge problem in the industry and that being very difficult to solve. How are you trying to disrupt the industry, especially in CFD using M-Star?
Oh, yeah. I mean, basically, I want every engineer to have M-Star at their disposal, because right now it's done by specialists. Specialist, we send it to the CFD guy and he'll run a 2D case on his desktop computer in 3 months, and he'll come back with an answer. CFD gets a rap of being, it takes a long time and it's expensive and you got to be a genius to do it. M-Star is none of that. I can run it on a laptop. You don't have to be a super genius to use it. It's very simple and it's very quick. So really, we want to disrupt industry by using the software that everyone, the hardware that everyone has. Everyone's got an NVIDIA GPU now because they're awesome. And we can leverage that to run crazy fast simulations that if an engineer is like, I wonder what the pressure drop is in that weird looking pipe that I don't have an equation for, I can just do it in M-Star in an hour and a half, and get my answer and move on. That's how M-Star really should transform everything.
Yeah, I think you guys will definitely achieve that. But I'm just wondering, in a market that's so crowded with different CFD tools and different types of software, and also the big players like Ansys, etc., how are you trying to achieve that? And do you think that's even possible?
Yeah. So the guy who's behind all that, his name is Brian Devincentis. He's the solver guy. So what's crazy is M-Star is written by basically one guy. He's the solver guy, and so. Yeah, he has a limited bandwidth, but he also knows how it all works together. So we basically continuously feed him industrial problems that he can implement in his solver. So the benefit of the M-Star team is how fast they can develop, how fast they can put physics into the solver. I mean, I asked John for heat transfer. He's like, yeah, we can do it. Like 3 months later, they had to implement an entire, heat transfer algorithm on top of their Lattice Boltzmann solver. Like, what? Who does that? Typically with you put in a feature request, it disappears into some email, and 3 years later, hopefully it shows up in a change log, the thing you asked for. But with M-Star, you're talking to the people that write the software.
Yeah. How big is M-Star right now? How many people are there?
I think it's 4 people. So M-Star was acquired by Dotmatics, and Dotmatics is a big software company. The core team at M-Star is John Thomas, the CEO, president, Brian Devincentis, who's the solver guy, Kevin Smith, who's actually the co-founder. He likes to not be as visible as John, but he actually is an excellent programmer himself. He writes he writes the pre and he writes post, and he also handles all the like architecture. So he's like head of software architecture. And then Eric Jans is the support guru. So he came from Kim and Ear. He's been there for like 25 years. So he's an agitator expert. So it's basically just 4 people, right? So that's kind of the core team of M-Star. Yeah,
that's pretty cool. I want to go back and to kind of giving advice for aspiring engineers and entrepreneurs. How would you pick it? Let's say you would start from scratch again. What industry would you pick and why? Like how is your thought process going in terms of like picking a specific industry? How do you solve a problem? How do you approach problem solving? How would you do that? How would you think about that?
I don't know if you can if I intentionally just picked an industry. So I actually, when I was at Georgia Tech, I took one lab on pressure vessel analysis where we put strain gauges on a Coke can and we put some air pressure in it. And I remember thinking, this is boring. This is the worst thing. I hope I never do pressure vessels. And then I graduated in a recession and the only job I got offered was pressure vessels. So I took it. But then I ended up enjoying it so much because it's FVA and it's calculated. It's not a Coke can with air in it. And then I discovered the problems. So if you're starting off like a college guy, like, oh, I want to start my own business, I don't know if that's the right way to do it. That's not how I did it. I think you have to get into industry and then you kind of have to look around and see, okay, what is costing these people a ton of money and how can I use my brain to fix it and save them money? Because if you save, that's the easiest sell in the world. I'm not a salesman, but if you can say to someone, if you spend 10 grand, I'll save you 100. I mean, that's kind of easy. That's an easy sell.
Why do you think LATTICEPT is so much better or so much more advanced when it comes as compared to other CFD consultants or like simulation consultants?
Well, I'm the only one using M-Star. That's kind of my secret weapon is that I use M-Star CFD, so I can do simulations so fast compared to other people. I'm also I have a wealth of knowledge in different industries. I don't like to toot my horn too much, but I originally went to school for welding, and then I went to pressure vessels, and then I was a consultant, and now I sell software. I taught myself programming when I was 9 years old. So I have just a bunch of different knowledge across a wide range of industries, and I know how to take the tools and solve problems. That's the main benefit of LATTICEPT. There's not 100 people. I don't have a bunch of consultants. I don't want to grow to be 1 million people. I want to stay a core group of really good engineers solving the hardest problems. That's my goal.
Mm-hmm. Do you have kind of a special agreement then with M-Star where you're the only one who is able to use M-Star for consulting purposes?
I'm not the only one that can use it. I'm just the only consultant right now that uses it. There's most of the buyers of M-Star, users of M-Star, are people that are making things. The Sherwin-Williams of the world. They don't take outside projects from random chemical companies. M-Star is kind of the secret, in industry. Pfizer's, I think one of our larger clients, they use that internally to make their drugs. They don't want to tell someone else that that's what they're using to make the drugs because that's part of their secret sauce, So that's kind of, the main thing of LATTICEPT is I can use M-Star to solve anyone's problems, not just your own internal ones.
Yeah. What I noticed also in other interviews is that you're very well spoken, so you know how to communicate. So how important as an entrepreneur is it to be a good communicator?
I mean, it's probably the most important thing. And that's one thing about John Thomas too. He's really well spoken,
He's really good. Yeah.
Yeah. I mean, you talk to him, you're like, oh, this guy knows what he's saying. And you kind of have to project that confidence. And I think to get people to understand you. So, and it go back even to the Challenger disaster where they had, I really took this to heart when I was in school. I took a class about engineering ethics. So they showed me the paper that the guy had written about the O-rings, and it was pages and pages of calculations. But there was no one really explicitly stated like, hey, don't fly the space shuttle. It's going to explode, right? Because an engineer's first thing is to say, oh, well, what people need to see is the calculations. If I show them the calculations, they'll get it. that's not how it works. You have to start with a message and then use the calculations to back up your message. And I think that's the most important thing. And it takes a while to learn that. Yeah.
How do you hone your skills, like especially your soft skills? Do you do it actively still, or is it just happening on the side while you sell stuff?
You mean software or communication?
Communication.
Oh yeah, I think it's just a natural thing. You also have to know when you're not good, and that's also the hard part. When you sit down and replay those scenarios in your head, which everyone does, and say, "Well, I should have said that," or I that wasn't the right way to approach it in retrospect. I think you really have to be introspective and really think about how you could have communicated better, and that's really the best way to do it. You have to get out there and do it. That's really all there is to it.
Mm. When we talk about the future of CFD, maybe some predictions from you, Ben, how do you think ML, AI, GPU-based codes will impact the simulation world?
I think we use the words new industrial revolution. People think that's kind of, it's kind of gimmicky. I'm not sure it is, because now we're seeing GPUs accelerate so fast, and that's M-Star kind of got lucky in the fact that we're just kind of traveling up this AI wave. We don't do AI yet. But we're basically taking this NVIDIA wave upward. And so M-Star is just going to get faster as NVIDIA gets faster. So we're going to get so much faster doing bigger simulations just as NVIDIA gets faster and faster. Now, the CFD world in general, I think graph neural networks are huge, huge benefit that we're going to see in the future. I think we'll be able to predict all sorts of things. And I don't know if you've seen these deep ONet models from Google came up with them. They can actually, they came up with a neural network to collide particles together. So it's I think we'll be able to use these tensor cores to do all sorts of physics that we can't even do right now, even faster. Another huge thing, I don't even know what to think about this, is these quantum computers. When you can run a simulation faster than real time. So let's say you wanted to simulate an hour of flow and you can do that in 10 minutes. I mean, that's totally different. I don't even know, typically it's going to take multiples of time to run a simulation. But when we can literally we can iterate over thousands and thousands of different problems to find the most optimal solution. That's going to be the future of CFD. It's really about optimization. Yeah.
But then the question also is at what point is it not practical anymore to run a simulation in 2 minutes? Because the other departments have to catch up with design and whatever it might be. So I'm not sure what the point of diminishing return is. So
I think engineers are pretty good at leveraging the tools they have. Well, some of them are. I really think optimization is going to be the future, and it's already happening now, but we're going to have topological optimization. So in the future, I'm going to be able to say, oh, M-Star, I want, I can't exceed this pressure drop and I'm trying to transfer the most heat, go. And it will fill in the solution space with what the geometry looks like. Yeah. And then we'll probably 3D print it and, off we go, all in one building.
Super cool. Any closing remarks from your side, Ben? Anything we might have not mentioned in this podcast that you definitely want to mention in this show? I feel like we rushed through it in half an hour.
Yeah, I didn't mean to rush. I just started talking. I guess my question really for you: how did you get into this gig? I mean, you just decided that engineers aren't good at selling themselves and you can do it better? I mean, I think you do a good job. I'm just curious how you got into doing this.
Yeah, I started actually at SimScale. So while I was studying, I was working for SimScale, started off as an FAA simulation assistant, and then somehow went to the dark side of marketing, started running the community there, did some product marketing, content, SEO, website work. So basically everything, as you mentioned, be more like a generalist. And then at some point I was like, I can run the shit myself. And this is how I started Apex. So we run marketing campaigns, optimize sales for some companies. So been going pretty well so far. So it was kind of was just a coincidence, I guess.
Yeah, I think, I watch your stuff on LinkedIn. It's great.
What's the plan for LATTICEPT in the future, next 5 to 10 years? Any plans?
Yeah, so I just partnered with my pressure vessel shop in Alabama. Mm-hmm. So I have our small R&D facility outside of Atlanta, but And Alabama is the big shop. And so we're going to start developing and selling our own pressure vessels basically for world delivery. So Mobile, Alabama is right on the port. I can ship one to you if you wanted to, because we can just put it on a boat. So the next big thing is really LATTICEPT is going to start selling industrial equipment to the world. So now we're just going to be analyzing someone else's industrial equipment. We're going to be calculating, simulating, fabricating, and selling, actual industrial equipment using all these fancy tools. Yeah.
Excellent. How can people find out more about LATTICEPT, and where can we find you guys next, maybe on an event?
Yeah, so we're going to FabTech in October. Mm-hmm. That'll be the next event we'll go to. And then next year we'll be at Downstream USA, which is the oil and gas symposium. So even if you don't, FabTech is just neat. If any engineer has never been to FabTech, you should probably just go, because they have literally floors and floors of robots and CNC machines and lasers and all sorts of stuff. I mean, it's just cool to see. Yeah.
Excellent. If people want to find out more about LATTICEPT, I'm going to put every relevant link in the description. And then people, if you want to connect with Ben, I'm also going to put your LinkedIn profile in the description as well.
Sounds
Ben,
great.
thank you so much.
Thank you.